Alright guys, I want to look at the 2012 number 2 problem that you had for homework together, just to kind of make sure we're on the same page and to answer any questions you maybe have. 2012 number 2 says that a sample of a pure gaseous hydrocarbon is introduced into a previously evacuated rigid 1-liter vessel. The pressure of the gas is initially 0.200 atms at a temperature of 127 degrees Celsius. And the first thing we're asked to do here is to calculate the number of the moles of the hydrocarbons. Now you may see moles and think, oh, I have to do stoichiometry, but there's no grams and we also have an unknown hydrocarbon, so that's not going to work anyways. So instead, we pay attention to the fact that this says gas up here, and we're given pressure and temperature and volume, which should be a dead giveaway that we're going to use PV equals nRT, where our pressure is 0.200 atms. Our volume is 1.00 liters. N is what we're trying to find. R is 0.0821. Oops. Let's try it again. 0.0821. And 127 degrees Celsius plus 273 to get it into Kelvin is going to be 400 Kelvin. So we go through, do our math. 0.200 times 1 gives us 0.200 divided by 0.0821 and then divided by 400 gives us a 0.00610 moles of our hydrocarbon. We're going to keep 3 sig figs in our answer because we have 3 in the 1.00, 3 in the 0.200, and 3 in the 127. I know you may see that 400 and think 1, but always go back to that original number. Okay, so that's A. Easy peasy. Moving on. Oxygen is then introduced into the same vessel containing the hydrocarbon. After the addition of the oxygen, the total pressure in the gaseous mixture is 1.40 atms at 127 degrees Celsius. Calculate the partial pressure of O2. So first thing we see hydrocarbon, oxygen, and maybe we're thinking combustion reaction, but notice it hasn't told us a reaction has occurred, so we're not dealing with a reaction just yet. Instead, what we're dealing with is a partial pressure where the total pressure in the system is going to be the pressure of our hydrocarbon, which I'm just going to abbreviate HC, plus the pressure of our oxygen. So let's see what we know. We're told that the total pressure in the container is 1.40. Okay. If we go back up to the original part, or the original prompt, we're told the pressure of the hydrocarbon is 0.200 atms. Okay, and that hasn't changed because we're still dealing with the same temperature. And that's going to be part added to the pressure of the oxygen. And what we end up getting is the pressure of the oxygen is going to be equal to 1.40 minus 0.2, so 1.20 atms for our oxygen mixture, or for our oxygen in the mixture. Okay, so again, pretty straightforward. Then we get to the reaction. The mixture of the hydrocarbon and oxygen is sparked so that a complete combustion reaction occurs, producing carbon dioxide and water. The partial pressure of these gases at 127 degrees Celsius are 0.600 atms for carbon dioxide, 0.800 atms for water. There is oxygen remaining in the container after the reaction is completed, meaning this guy is in excess. So keep that in mind as we're going through this. Use the partial pressures of CO2 and H2O to calculate the partial pressures of the oxygen consumed in the combustion. So this is where we do get a little bit of stoichiometry, but also keep in mind that when we think back to Avogadro's law, we can use volume, pressure, etc. just like we would mole values because we're keeping in the same temperature and in the same basic volume. So our ATMs here, our pressures, can be used just like they would be for a mole value. Also notice we can't just write a reaction here because we really don't know what our hydrocarbon is. It's CXHY. We don't know what X and Y are, plus O2 is forming CO2 plus H2O. We don't know what any of our coefficients are, so we're not really going to be using a reaction per se here either. It's not going to work well. Okay, so what do we do instead? Okay, well, 0.600 atms for CO2, we can convert this into O2 by recognizing how many O2s are used to create CO2. And for every 1 mole or 1 atm, you can technically use either or because we are using that Avogadro's law idea. So 1 atm of CO2 would require 1 atm of O2. So kind of look at our ratio of here of CO2, 2 oxygens, to O2, 2 oxygens, which means 0.600 atms of O2 was used to make 0.600 atms of CO2. We'll do the same thing with the water. 0.800 atms H2O, and again, notice all I'm doing is using my pressure just like I would a mole value, and that is because we're able to do that understanding the relationship to pressure and moles and temperature and volume and all that stuff that Avogadro helped us with earlier. Okay, so 0.800 atms water. We can do this one of two ways, or we can say for every 1 atm water, there we go. We only have 1 oxygen, so we only need a half atm of O2, or I prefer not to deal with fractions in that regard, even though it ends up being the same thing regardless. I would set it up that for every 2 moles, or 2 atms, sorry, I keep switching back into moles, but it is the same thing in this case because of what we're dealing with. 2 atms of H2O would give us 2 oxygens, so that would leave us with needing 1 atm of O2. So you're still multiplying by 1/2, and it works the same way. Okay, and that's going to give us 0.400 atms O2. So what we've done is found the amount of O2 needed to make our CO2, the amount of O2 needed to make our H2O, and what we're being asked to is the total consumption, which is going to be these two values added together, so 1.00 atms O2 is our total value that was consumed of our original 1.2 atms. So there is still 0.2 atms left over. Keep that in mind, that's going to come in handy a little bit later on. Okay, so from here, on the basis of your answer above, write a balanced chemical equation for the combustion reaction to determine the formula of the hydrocarbon. Okay, there's a couple different ways you can do this. First and foremost, what they're really asking you to do is find an empirical formula or a molecular formula for our hydrocarbon, which means you could go into moles and do your mole ratios, or you could recognize that our ATM ratios are also very similar to our mole ratios. So if we grab our reaction that we kind of wrote up here, CXHY plus O2 makes CO2 plus H2O, and remember that we had 0.200 atms of this guy, which you can grab up from the top of the problem. We just calculated this as 1.00 atms oxygen that was used, and again, we know all of this was used because we're not told any of it's left over. We are told oxygen is used, and there's some left over, so not all of the 1.2 is used, only the one we calculated up here is. We're told that this is 0.600 atms for our carbon dioxide, again, that's just the number above us, and 0.800 atms for our water. So if we treat these like we would a mole ratio, kind of like what we did with empirical molecular formula, and we divide by the smallest value, which would be our 0.2, we can get a whole number balanced coefficient for in front of our balanced chemical equation and backtrack that to calculate what x and y actually is. So if we divide 0.2 divided by 0.200, that's going to give us a 1. We divide 1 by 0.200, and that's going to give us 5. We divide 0.6 by 0.200, that's going to give us 3. And we divide 0.8 by 0.200, and that's going to give us 4. Now, what does this tell us? That tells us that there were 3 carbons and that there are 8 oxygens, which means C, X, and HY have been calculated. C is going to be 3, or X is going to be 3, and H is going to be 8. Okay, if that makes any sense, kind of how to do that. You can, again, do it mole value if you want. I can walk you through how to do that. Pretty simply, basically, you would take your 0.2 atms, get it into moles, your 1 atm, your 0.6, your 0.8 into atms, get those all into moles, and then do the same basic idea with your mole ratio. But if we can use our ATMs, it does save us a step. And again, we can use ATM because of the relationship PV equals nRT, as long as our volume staying constant, temperature staying constant, R staying constant, our moles and pressure, okay, are going to have the same basic relationship. So we can use moles and pressure pretty well synonymously throughout this type of problem. Okay, part E. Calculate the mass of the hydrocarbon that was combusted. So, not too bad. We already know what our hydrocarbon is. And if we jump back all the way up to A, remember we calculated the amount of moles. 0.00610 moles. Now we get to do our stoichiometry. Okay, so C3H8. And we're going to calculate that into grams, which means we need our molar mass. Okay, well, with carbon, we have 12.01. Remember, you are supposed to go out to the 2 decimal places with AP. Times 3, 1.01 times 8, and we get a molar mass of 44.11 grams. So we do that math times 0.00610. And that's going to give us a total gram value of 0.269 grams of C3H8. Pretty straightforward. All right, last problem on here has nothing to do with gas laws per se, but it does fall back into our reaction chapter. And we need to be comfortable with this idea of moving back and forth between different concepts and kind of getting a basic idea of the fact that in many cases our AP level problems are going to be a combination of multiple concepts. It's never just going to be one thing, or very rarely is it just going to be one thing. So you have to be able to shift gears pretty quickly and pretty comfortably. So let's look at F. As the vessel cools to room temperature, droplets of liquid water form on the inside of the walls of the container. Predict whether the pH of the water in the vessel is less than 7, equal to 7, or greater than 7, and explain your prediction. Now, I will say this is a little bit of an older problem where predicting products was more prevalent, but I still kind of want to work through it and kind of get a basic idea. So if we think back to our reaction, which we had in the previous problem, we have the reaction of C3H8 plus O2 going to CO2 plus H2O. And remember, after this reaction has occurred, all of our propane, C3H8, has been used up. We do have leftover oxygen. The water, we're told, is now condensing into a liquid, and we have carbon dioxide. So we kind of think about this type of reaction and see what's going on. First off, do oxygen and water interact with each other? No. Okay, but our CO2 and H2O do react with each other. If, again, we remember back to our reactions that we discussed way back when in honors chemistry, our predicting products. So a water and a non-metal oxide is going to produce an acid, was one of our trends or patterns that we were supposed to know way back when. Again, this isn't so true on the new exam, but I do want to just kind of break it down and talk about it. So H2O and CO2, the acid is going to produce is H2CO3. Our carbonic acid. From there, once you recognize that this is an acid, this is pretty easy to figure out. Predict whether the pH will be less than 7, equal to 7, or greater than 7. And since we have an acid, we know that it is going to be less than 7. Explain your prediction, because we have an acid, H2CO3, being formed, which means it is going to produce, if we think back to our acid reactions, it is going to produce our hydrogen concentration. And if our hydrogen ion concentration is increasing, our pH is decreasing or becoming less than 7. Okay? All right, guys, that is a 2012 number 2 problem. I hope it helps. If you have questions, either let me or Mr. Christie know. Thanks, guys.